Okay, so the purpose of this particular session is to go over the review problems for the exam. So let's get started with that. Okay, so in problem one, we want to know how many ways can eight people be seated in a row in part A if there are no restrictions on the seating arrangement. Well, that's just a permutation, 8 factorial. In part B, we'd like to know how many ways to do it if A and B, two persons A and B, must sit next to each other. So what I'm going to do is consider A and B as a unit. So we'll put them, and so how do we do it? Well, if we consider them as a single unit, we're going to put them in the same seat for now, and then we're going to split the seats. So there are, instead of 8 seats, there are 7 seats, and we're going to put A and B in one of them, and then we're going to split it up. And on one side will be A, and the other side will be B, but you can also reverse the order. So if you think about it, if you consider A and B as a single unit, then there are 7 units total, the unit consisting of A and B, and then everybody else. So there are 7 factorial ways of seating the units, but then there are 2 choices. We could put A to the left and B to the right, or B to the left and A to the right. So it's 2 times 7 factorial is the answer to this part. C. There are 4 men and 4 women, and no 2 men or no 2 women can sit next to each other. Okay, so in that case, we have to consider 2 cases. Let's consider the case where so think of the 8 seats. 1, 2, 3, 4, 5, 6, 7, 8. We could put a man. Suppose we put a man in the first seat. Then if no 2 men can sit next to each other, then the next place you can only put a man. You can only put a man in an alternating way. And how many ways are there to put the men? Well, in those slots, well, there are 4 factorial ways to put the men in. And then the women go in the other slots. This is if the man goes into the leftmost seat. So there are other 4 factorial for the women. So it's 4 factorial times 4 factorial if we seat a man first. And then likewise, if we do a woman first in the leftmost seat, then it would be woman, man, etc. We would also get 4 factorial, 4 factorial. So 4 factorial for man first, and 4 factorial for woman first. So the answer should be the sum of these two, which is 2 times 4 factorial times 4 factorial. So that's the answer to that question. You can compute what that is as a number, of course, but I don't require you to. Okay. Okay, so in part D, it says there are 5 men. There are 5 men, and they must sit next to one another. So how could that work out, right? 5 men sitting next to one another. Well, so how can we put the 5 men in? Well, we could put the man in the first slot, and then it'll be man, 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 and then all women. Or we put the man in the start the first man in the second slot, man, 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 and so on, right? So let's take the first case, okay? The first case, we have how many ways can we put the men in? Well, there are 5 factorial ways to put the men in those slots, and then the women go in the remaining slots, and there are only 3 factorial, 3 women to be put in, so it's 5 factorial times 3. So if we, in the second case, so this is case 1, in case 2, we have the men here, that's 5 factorial ways, because we can permute those men amongst themselves, and then we have to put the women in the remaining slots, so that's 5 factorial. Well, you can see what's going on. I probably need more room, so let me save the drawing. and erase some. So the other configuration is we can put the first man in the third slot. So the man could go here, and then it's man, 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 man. And it's again 5 factorial times 3 factorial. And there's one other case where the man starts off in the fourth slot, and that would give me another 5 factorial times 3 factorial. So man. So it would be 4. The answer should be in part D, the answer should be 4 times the 4 possibilities times 5 factorial times 3 factorial. So that should be the answer, which you can think of also as 4 times 3 factorial as 4 factorial. So it's 5 factorial times 4 factorial. Okay, so that's part D. Now let's do part E. So in part E, we're talking about 4 married couples, and each couple must sit together. So we're going to treat each couple as a single unit, and then there are 4 units. So, maybe man, woman, man, woman, man, woman, man, woman. And we're taking those couples and we're putting them in a slot, and so they occupy, think of each slot as 2 seats. And now you could put the man to the left and the woman to the right in each slot, or the woman to the left and the man to the right. So that gives you 2 possibilities for each slot. So first of all, you could put each of the couples in a 4 factorial ways of arranging the slots. You can put them in one of the slots, and then each slot you can arrange in 2 different ways, putting the man on the left or on the right side. So it would be 2 to the 4th. You'd be multiplying it by. So the answer is 4 factorial times 2 to the 4th power. Okay. So that is the solution to problem 1. I'm going to move on to problem 2. Okay, so the problem says from a group of 8 women and 6 men, a committee consisting of 3 men and 3 women is to be formed. How many different committees are possible if A, 2 of the men refuse to serve together in part A? So how does that work? Okay, so if 2 of the men refuse to serve together, that means there are 2 possibilities. Either none of those men that refuse to serve together, neither of those men are on the committee. And how many ways can we choose then the committee? Well, we have 3 men that we have to choose out of 6 men, but we're not choosing those 2, so it's really 6. So we throw away those 2, we're left with 4. So it's 4 choose 2. 4 choose 2. No, sorry, not 4 choose 2. We're choosing 3 men. So we're choosing 4 out of the 4 remaining men. We're choosing 3. So it's 4 choose 3 of the men, and now we have to choose the women. There's no restriction on the women in part A, so it should be 8 choose 3 possibilities for the women. So that's if neither man is on the committee. And then what if one of the men is on the committee? Well, it goes like this. If one of the men is on the committee, then one of those 2 is chosen. And now we have to get the remaining choices from the other 4 men out of the 6. So it's 4 choose 2. And then we have to choose the 3 women, A choose 3. Again, there's no restriction on the women. So that's the other possibility. That's it if exactly one of the men is on the committee. So if we add these together, we get exactly the number of ways of choosing the committee in which 2 of the men refuse to sit together. Okay, a similar argument goes for part B with women. Suppose two of the women refuse to sit together. Well, if two of the women refuse to sit together, suppose we have a situation where neither of the women is chosen. If neither of the women is chosen, that means we're choosing 3 out of the 6 remaining women. And then we have to choose 3 of the 6 men total. And that's with neither woman is chosen on the committee. And then you could, what about the case when one woman is chosen? Well, if one woman is chosen, you're choosing 1 out of the 2 that are fighting with each other. And then we are choosing the remaining 2 women from the remaining 6. So it should be 6, choose 2. 2 of the remaining women, 2 of the women are being chosen from the 6 remaining. And then we have to choose the 3 men. That's 6, choose 3. So that's the answer for part B. Okay. So now, what about part C? One man, and one woman refuse to serve together. Let's work it out over here. So there are several cases to consider. Suppose neither party serves first. If neither party serves, how many choices are there? Well, if neither party serves, that means we're not choosing one of the women from the 8 women, and we're choosing 3 women, so it's 7, choose 3. And we're not choosing one of the men, we're choosing not from 6 men, but 5 men, because we have to leave 1 out. So that's that case. If only the woman serves, what we get is, what do we get? Well, if only the woman serves, that means we're choosing. Okay, so if only the woman is served, we already reserved a spot for that woman. And then we have to choose the remaining 2 women from 7 women, so that the women are coming from 7 possibilities because we already have one of the women. And then the men are being selected. We have to leave one of the guys out. So there's only 5 men to choose. Out of 5 men, we have to choose 3. So that's if only the woman serves, and if only the man serves, it's a similar calculation. In that case, we're choosing the 3 out of the 7 women, and we're choosing 2 out of the 5 men because we already have 1 man there that we've already selected, the man that is fighting with the woman. So we have to add these 3 numbers together, and so I'll put plus signs, and we get the answer in part C. Okay, an urn contains 5 red, 5 red. I'll indicate it that way. 6 blue, and 8 green balls. A set of 3 balls is randomly selected. I guess the assumption is that we are not, initially we're selecting them without replacement. And then we're supposed to redo the problem with replacement. Okay. So the part A is saying, what is the probability that each of the balls will be of the same color? So, well, let's choose one of the colors. So say red. How many ways are there of choosing 3 red balls? Well, 5, choose 3, if all red. What if they're all blue? That would be 6, choose 3. Or what if they're all green? That would be 8, choose 3. So that's the number of ways of choosing balls. Ways of choosing balls. All balls of the same color. And now, how many ways are there choosing 3 balls? Well, there are 19 balls total, and you'll be choosing 3 out of 19. So that would be the denominator of the answer. So that's the answer in part A. In part B, what about different colors? Well, Let's think this through. Suppose we first choose a red ball, then a green ball, a blue ball, then a green ball. So that in that order, right? So how many ways are there first to choose a red ball? We would choose 1 out of 5 choices. And then how many ways are there thereafter to choose a blue ball? Well, that would be 6 choose 1 choices. And how many ways are there to choose a green ball afterwards? So this is the number of ways of choosing first a red, then a blue, then a green. If we were to reverse the order, like permute the order, blue, red, green, for example, you get the same answer. The numbers that I just got are just permuted. So how many ways are there to permuting the colors? 3 factorial ways. So this is the number of ways of choosing 3 balls, all whose colors are different. And so if you want to get the answer will be, the answer to this part B is 3 factorial times 5 times 6 times 8 over the number of ways of choosing 3 balls, which is 19 choose 3. So that would be the answer to part 2, part B of the problem. Okay, so that's sampling without replacement. What if we wanted to answer the problem with replacement? So I'm going to do that now. So let's do the version of this problem with replacement. It's not much harder. So if we do this with replacement and we want to select balls of the same color, well, we're going to let's suppose we first choose a red ball. Then we have to choose a red ball the second time and then the third time. How many ways? We take one red ball out and then we put it back in. So there are 5 ways to choose it the first time. And now since we put it back in, there are 5 ways to choose a red ball the second time, and then 5 ways the third time. So in other words, 5 cubed ways of choosing 3 red balls with replacement. Now, if we didn't choose a red ball, we chose a blue ball, that would be 6 cubed. And if we chose a green ball, that would be 8 cubed. So these are the number of ways of choosing with replacement all 3 balls of the same color. And then if we choose balls with replacement, the number of ways to do it is 19 cubed ways. So this is the answer to part A, if we do it with replacement. And part B with replacement, we want to choose balls of different colors. Well, let's first assume we've chosen a red ball. So suppose we did red, blue, green. Okay, we first choose a red ball. We put it back in. How many ways are there to choose a blue ball? Well, there are 6 ways, as in the second case, and then there are 8 ways to choose the green ball. And now, on the other hand, we also have 3 factorial ways of permuting these red, blue, green. So it'd be 3 factorial ways of, so that would mean, like, for example, if we had green, blue, red, that would mean we first chose a green ball, then a blue ball, then a red ball. There are three factorial ways of permuting those three letters. And then on the bottom of the fraction is 19 cubed as before. So that would be the answer in this case. By the way, you don't have to give me an exact number. I'm happy with answers that look like this. It actually is easier to grade that way. Okay. Let's move on to the next problem. Problem 4. 5 people designated as A, B, C, D, and E are arranged in linear order. Assuming that each possible order is equally likely, what's the probability that there is exactly one person between A and B? Okay, so now let's think of it this way. Suppose A is, so A, B, C, D, there are 5 slots. Suppose if A is in the first slot, okay, that's one possibility. Then B would have to be in the third slot. Okay, so how many ways to seat everybody else? Well, there are 3 open slots where we have to put C, D, and E. There's 3 factorial choices here. Now, another possibility is A is in the second slot and B is in the fourth slot. So then there are 3 factorial choices that come about in that case as well, where we have to put C, D, and E. Likewise, A could be in the third slot, and then B is in the last slot. So A could be here, B could be here, right? And that gives me what? That gives me 3 factorial choices. Now, we can also reverse the roles of A and B in everything I did, and that gives me twice as many possibilities. So in other words, here, if in the given cases that I've already outlined, this would give me 3 times 3 factorial choices in this case. And now, since I can reverse the roles of A and B, I get 2 times 3 times 3 factorial. If you like, 6 times 6, or 36 choices. Okay, so that's the answer to part A. What about to part B? Okay, so in part B, we want to know we want to have exactly 2 people between A and B. Well, here are the options in this case. So we could put A leftmost, and then B would be here. That would be one option. And there would be 3 factorial cases in that case. And then we could put A in the second slot and B over here. That would be 3 factorial. So in this configuration, we would have 3 factorial times 3 factorial plus 3 factorial, so 2 times 3 factorial. But now we also can reverse the roles of A and B as before, and that would give me that would double the number, so it'd be 2 times 2 times 3 factorial. And I realize that there's a probability question, and I have to, in order to finally solve part A and part B, let's see, in part A, I got the number of possibilities, and I said it was 36. That's the numerator of our fraction. And how many ways can we sit A, B, C, D, and E? Well, that would be 5 factorial, right? Likewise, this would be 2 times 2 times 3 factorial, which would be 4 times 6 is 24 over 5 factorial would be the answer to part B. 5 factorial is 5 times 4 times 3 times 2 times 1. So what is that? That's 3 factorial 6, 24 times 5 is 120, right? So this would be 24 over 120. Okay, so that is part B. So part C, there are exactly 3 people between A and B. Okay, so 1, 2, 3, 4, 5 slots. If A is here, then B has to be here. Or the other possibility is B is here and A is here. Those are the only 2 possibilities. And what do you get? In each case, there are 3 factorial ways to fill in the answer. So it's going to be 3 factorial. So it's going to be 3 factorial plus 3 factorial. In other words, 2 times 3 factorial ways of seating everybody in that case, and that's divided by 5 factorial. And that should, I guess, what do you get there? I don't know. It should be it'd be 2 over 4 times 5. If I got this right, 2 over 4 times 5, which would be 1/10, if I got it right. Okay. So that's the answer to problem 4. Now let's move on to problem 5. Okay, so this is a problem number 5, I believe. So 5. And a 6-sided die is rolled 4 times. What's the probability that 6 comes up at least once? Okay, so let E be first of all, the event that 6 never comes up. in four times, right? So what's the probability of 6 never coming up in 4 times? Well, we performed the experiment once. There's a 5/6 probability of not getting 6 the first time. There's a 5/6 probability of not getting 6 the second time. There's a 5/6 probability of not getting 6 the third time, and likely 5/6 probability of not getting it getting it the last time. So the probability of E is 5/6 to the power of 4. Now E complement is the event that 6 appears at least once. Oops. So the probability of E complement is 1 minus the probability of E, which is 1 minus 5/6 to the 4th power. Okay, so that's about 0.517, which is at least it's a little more than half the time you could expect 6 not to appear. Okay, so problem 6. In a 7-card poker game, compute the probability of being dealt 2 pairs. Okay, so let's get started with it. So how are we going to get dealt 2 pairs? Well, you have to choose the value of each pair. You know, are we getting 2 5s and 2 7s? So there are 13 different values of cards, and so we have to choose 2 out of the 13 to build the 2 pairs from. Each one of those, from each one of the values, we have to choose 2 out of the 4 cards in that value. So it's going to be by the multiplication rule, 4 choose 2 times 4 choose 2. Now we have 7 cards total. We have to therefore choose. We've chosen 4 cards. 2 pairs make 4 cards. So we have to choose 3 more cards, and those 3 cards cannot come from the 2 denominations we've already chosen. So there are 11 denominations left, and we have to choose 3 cards out of the 11 denominations. Now each of those denominations gives me 4 choices to choose from. So 4 choose 1 times 4 choose 1 times 4 choose 1. And that is the number of ways of building 2 pairs out of 7 cards dealt to you. And then the denominator would be 52 choose 7, the number of ways of dealing 7 cards out. So that's part A. So part B is no pairs. I don't have to write that. How do we deal with that? Well, if we want to get no pairs, that means we have to choose 7 distinct denominations. So like say a 5, a 7, a 9, a jack, a 2, and a 1, I don't know. So we have to choose 7 distinct denominations. And each of those denominations has 4 choices we are allowed to choose from. So it's 4 choose 1 for each. So it's 4 choose 1 to the 7th power. And then we have, again, 52 choose 7 ways of dealing the cards out. So that is the answer to this problem. And I'm going to stop here. We're done with the review sheet. Good luck on the exam.